your component and the printed circuit board are combined, or where they joins with the solder. I will call that a joint. So what can happen if it's let's say it's a pretty long component like this through-hole transistor, for instance. If I place it through my circuit board, and I touch my soldering iron to it, and the solder then flows to the heated joints and then connects your component to the printed circuit board or the circuit board. What then might happen is that if the component then moves slightly, the joint might become cracked. Because what you will have to remember is that you're dealing with melted metal. And then there's a split second where the metal then goes from liquid to a solid. And if the component that you're trying to affix to the printed circuit board moves, then if it moves at the wrong time or during this hardening process, the joint might become broken or cracked. So what happens with a cracked or broken joint? Well, you will not have a very good electrical connection. Because the soldering that is probably then stuck or was stuck to the circuit board will probably lift up and become detached, and you will not have a very good circuit or very good electrical connection. And as the board moves around, that connection might become more broken and work less and less. And especially for, high frequency digital circuits, that become a bit of a problem. So you'll always, when you have a printed circuit board and you've soldered everything together, you will have to have a very good look to make sure that the joints that you have created are in good order. Right, so let's see if this camera actually works. I'm hoping that it doesn't interfere with this.
Hello? We can't hear.
You hear me now?
Okay.
So, I think what is happening is once I plug in my microscope, it somehow, I think what happens is when I plug in my microscope, it assumes the video and also the audio from my microphone on USB. So I have to figure that out. And in the next lecture, I will use it. I was hoping that I could use it now. Okay, so we'll leave that for now. And then in the next lecture, I will have it fixed and then we can have a good look at it. Shame, but so it is. Right. But thank you very much for letting me know. If you cannot hear me, that's good. Well, it's not good that you can not hear me, but when you let me know, that's perfect. Right, so let's just continue on with the slides and we'll talk about all this. So these are a couple of just a couple of examples of printed circuit boards which I could find. I mean, I like this one on the left because it's a very old Nokia phone. And
Hello? We can't hear. It's no sound.
yes, thank you. Right. I don't know what is happening or why. For some reason, my microphone is playing up a bit. I'll just make sure to keep an eye on it and make sure that my Microphone does not mute. Right. In any case, so let's share my screen again. So I like this because you can see the whole phone, basically the whole structure of the phone is composed of the printed circuit board. So not only does the circuit board provide the physical connection of the components, it also provides the stability or the physical form of the phone. So your printed circuit board, its primary use might be, well, is to connect the components, electrical components, but it's also it can also be the structure. And on the right side, this is a circuit or a printed circuit board model of, I think, an Arduino board, which this person slightly changed. And we will work with this or something similar to this. So on this right side, I can see that it is a double-sided board. The blue side indicates that the connections are on one side, and then those red lines indicates to me that it's on another side. So when we create these boards, this is what it should look like at the very end, or the design. And you can see these green dots are the connections of the board, and this should be something we should end up with. Now I'm going to talk a little bit about printed circuit board manufacturing, because there are quite a number of ways in which you can manufacture a circuit board. Right, I think I have solved my problem a little bit with the microphone. I'm just going to be checking to see if this works. I did quickly change something. Hopefully there should not be.
Hello, teacher. Your answer is no stable.
Right. Okay. So that means I have not fixed the problem yet. Okay, so I'll stop doing that because that just wastes a little of time. Right, so let's talk about printed circuit board manufacturing. There are loads of different ways of manufacturing a circuit board, but I will look at about 4 methods or 4 ways you can create your circuit board, and it goes from ones you can do at home and ones where you order a company to do it for you. Now I have to usually, before I give this information, I have to warn people that you should not do it without supervision of somebody who knows what they're doing, because you will be dealing with acid. So, but we'll talk about that, and I'll describe why it's not very safe. But if you have to, then you have to use it. Right. Right, so the first one is the what I call the manual method. It is the simplest and lowest tech way of making a PCB. It's not a very professional way of making a PCB. I will not do this and then create a product which I will sell for somebody. But if I just need a prototype of something, I might do it in such a way. We need a PCB, which is a non-conducting material covered with a layer of copper. So you usually buy these copper boards. They look like this. So you have a substrate and then copper on the one side, usually single layer boards. And just in case you weren't sure what a single layer board is, you have copper on the one side, substrate, and double-sided copper on both sides with the substrate in the middle, sandwiched, as we spoke about. So once we have a board with copper and then backed with substrate, now what we have to do is we have to remove the copper to form our lanes, our circuits. So just to give an idea, so let's have my circuit board like this. So the shiny bit is where the conductive material is, and all the bits where you can see the sort of like the brown elements where I've removed the copper. So I've created my circuit board, and that circuit board, I've created the sort of like the traces by simply removing copper and isolating that track that runs between my components. And that's the general idea of the manual method. So either there are a couple of ways of removing the copper. You can either scratch it with a knife or something like that. But usually when you just scratch off the copper, it's not a very clean or neat process. So there's another method that you can use. This method is called etching. This word right here, it's called etching. It is usually a very dangerous procedure because you use acid to dissolve the copper itself. So what you need to do is you need a laser printer, and then you need to have designed your printed circuit board schematic and then transfer it to a printed circuit board design. And then you print that out on a transparent piece of plastic, like here, top left. So this is printed out with a laser printer, specifically laser printer. An inkjet printer does not work. What you then do is you, by using a heat source like a iron, you melt this piece of plastic onto the copper itself. So what will happen is wherever you have these the melted bits of plastic, that is protected against the acid. So then you put the printed circuit board or the piece of copper inside a bathtub of acid, and then that would dissolve all the copper, but leaving the traces that you made with the inkjet printer. Now you can also buy this UV activated printed circuit board paper, which you also print on it, and then you just transfer it with heat. This is this blue element here. But what you're basically doing, the idea remains the same. You transfer your PCB design onto a piece of copper using heat. And then once you have transferred it, there's a link which you can follow if you want to see it, but I'll give you the presentation and then you can follow the link. So basically the step is we transfer our printed circuit board onto the piece of copper. We put it into acid, and then after the acid has dissolved all the copper that was not covered by our printed elements, this is now our circuit that is left. So you can see all the copper has been dissolved, and only our traces here on the right side, which we wanted to be left, are left, and that's the only thing that's left. So we have then created a circuit board. Then what you need is to have a drill and then drill out the holes for the components and then solder it. You can also use a permanent ink marker to color over these holes, just to add in more protection to make sure that the acid does not eat through the circuit. But this circuit, as you might see on this picture here on the right, it is fine, it will work, but it's not the neatest circuit. You can't be exactly 100% precise by using these methods, and is pretty dangerous. Acid, and if you spill it on yourself, you will get burned severely. So this is a relatively low-tech approach to creating a printed circuit board. And when I was going through university, that is where they taught us to create circuit boards. But nowadays, it has become a lot cheaper to have somebody else so what happens, you create your circuit board, your printed circuit board, and then you send it away to a company, and then they manufacture your board for some machines. It has become really easy and really straightforward to do this, and also cheaper than buying the copper and the acid and so on and so forth. So I tend to show students or just tell them about the manual method of how you can how you can create a circuit board by yourself at home if you needed to. But nowadays it's not really necessary, because there are so many companies out there that can create your board for you. What you do is you email your design, they give you a quote, which is generally not that much that expensive, and then they manufacture your board, and then within a day or 2 days they mail it back to you, and you have your board inside of an envelope. So I wouldn't recommend using the manual method, as I've talked about. I would rather recommend finding a company close to you that would make your board for you. When I was studying, I found a company quite close to me. Boards for me. I send them the file. They create the circuit board and then mail it back to me, and it works perfectly. So I'm sharing my screen again. Right, so there are more or less 3 types of machines that can create a circuit board. Well, there might be more, but we'll talk about the one other machine that you might encounter. One is a milling machine, a laser, and then a mass etching machine. So a milling machine is basically a drill. So you have this machine on the right side. You place in a copper plate with substrate. And then this machine has got a number of very, very small drills that it uses to drill into the copper and remove the copper itself. So it drills away the copper instead of dissolving it, leaving you with your printed circuit board like here on the right, and then also cuts it out and also drills in all the holes for your components if you need holes drilled. These machines sometimes are relatively small, that ones that can like as big as a little laptop computer, some of them, and then some of them as big as a desk, and then some of them even larger than that. They are really good at making boards, but they tend to take a long while, because they physically have to select the correct drill, use that drill to make very precise marks on your copper board, and then drill very precise holes. And sometimes that can take a very long time. There is also the next upgrade to this would be a laser machine. So instead of having a drill, you would have a physical laser that burns off the copper. And then you have a mass etching machine. So this machine does what we mentioned in the manual creation of printed circuit boards. So on the one end, you will have a printer or device that transfers a design onto a big slab of copper. And then it goes through a a big acid bath and then through a drilling machine, and then we end up with a whole bunch of printed circuit boards. Generally, that is what this is a bigger industrial sized operation. So, I mean, if you're lucky enough to have a printed circuit board machine, most probably you will have a milling type machine, because they are a lot of times they're the most common and sort of like the easiest to maintain. But then you can make a small number of boards, and sometimes they take a bit longer. More expensive machines will use a laser to burn away the copper, and then the big industrial machines, more often than not, they use a big industrial etching process. So with that as well, we have the fourth type of machine that nowadays has become a little more prominent is a 3D printing machine. So all of these methods, the only way we can really create circuit boards is by we start with a slab of copper and then take away the copper we do not need to isolate our tracks and make our electrical connection. And that is called, like, I think, subtractive manufacturing, because you're subtracting material from your workpiece. But you can also have a 3D printer, which on the substrate itself prints the circuit itself. Now, I haven't really seen machines that do this on an industrial scale. They might be out there, but usually it's more of an interesting or a unique type machine that people have. Well, you can also use a 3D printer to create a circuit board. And yes, you can. But you cannot create a very exact type of machine. You cannot create very, very small tracks. So a lot of these tracks might be like a 1/10 or a 100th of a millimeter wide. And with a 3D printer, that's really hard to do. So yes, you can have a 3D printer creating a printed circuit board, but then with the added sort of disadvantages, sometimes it might not be a very good printed circuit board. But as technology advances, who knows what we're going to end up with in terms of creating printed circuit boards. Right, I'm sharing my screen again. So there, by using a PCB machine might have some advantages that a handmade board does not have. And one of them, you cannot really create a multi-layer board without using machine. Remember, we spoke about having a multiple layer board. This is one of the so like an example of a multiple board. So this on the left, it's a multi-layer PCB, and on the right side, you can see you will have the connections or the substrate, and then copper connections between these layers connecting multiple layers. And we spoke about if you have very difficult to connect boards or a certain integrated chip with lots of connections close to each other, you will have to use some sort of multi-layer board to facilitate the connection of those layers. And that is more easily or more readily done by a machine than you can really do it by hand. Most machine-made PCBs are covered with a resin, and this resin is called a solder mask. Okay, let me just switch this off. So this is a printed circuit board, and it is the circuit is, you can see the circuit lines running, and it is covered in this bluish epoxy material. It can be an epoxy, a resin, a plastic, a rubber, anything that is non-conductive. And the main function of this covering is just to protect the circuit on the inside, so that if somebody touches the circuit with their finger or any other conductive material, that you do not short between these lines. Because, okay, I'll show you on the I'll show you next time on the microscope. Sometimes the connections are really, really close together, and it's very easy to short them. So we generally coat them if you buy a circuit board with some sort of non-conductive material. And most of the time, it just looks nicer. Now, this material can be red, green, blue, black, whatever kind of color you want it to be. As far as I'm aware, there is no convention to the color of a printed circuit board. It can be whatever you want. Older circuit boards generally went with the green covering. I don't know. If you have an Arduino board like this, they're quite often blue. Other companies have a red board. It doesn't really matter. You can choose whichever color of resin you like. And I'm sharing my screen once again. And as you can see, so the green bit is the solder covering. Here we have a trace running between our two connections. And these connectors are now what we attach our component and our soldering metal to. So you would attach your solder iron onto there and touch a bit of solder iron, it will melt and connect it to that. Now, there are also other little terminologies, but we won't really get into it now until we get into inspecting a printed circuit board after you've manufactured it. Like the last element in PCBs is called a silk screen. What is a silk screen? It is a layer of information about the printed circuit board. So it is this white writing that you can see on this board. So what does this do? Well, this board, a couple of things about this board. You can see that there are connections between elements, and then you can also see the connectors are sort of like a silvery color. What that tells us, now this board is made with copper, but this does not look like copper. And what that tells us is that the connectors or the pads, we call them here, these pads are covered in some other material, like, for instance, tin, which protects the copper from oxidizing. It uses a green resin solder mask, and it's got a silk screen. And what is a silk screen used for? Water. The silk screen is used to give us information about the connections and the components that we have to connect. So here we have SW5. That tells me this is switch number 5. D1 is quite probably a diode one. You have a 9-volt connector, a capacitor 1, C1 and C2. So whenever you assemble your board, you can use the silk screen to help you identify which components you have. So when we get into the printed circuit board design, once you create your schematic of electrical components, every single one of those components will have a unique name or designator. Usually resistors start with R1, then you have 2, 3, 4, 5, 6, and 7. Capacitors usually start with C1 and so on. Diodes, D1. Inductors, I think I. Connectors might start with a J, switches with an SW, and they would all have this designation and then a number. Then with your printed circuit board design, you would have a printout or a list or a table with all of these designations of your components, R1, and then telling what that component is. So I will see R1 is a surface mount 120 ohm resistor. So then I know, okay, I take my component and I insert it into those holes designated to me by my silk screen. Silk screens are generally there to help people who are assembling the board for you, or if you need to perform maintenance on the board. Because now you have to remember, a lot of the times you might design the board, somebody else will manufacture the board, and then somebody else will then construct the board or insert all the components and solder all the components, and then it'll be shipped out as a product. Maybe down the line, somebody else will then either repair or refurbish or maintain your design. Diode, then this diode performs this function, and it is this value, this specific model number, and then they professional design, relatively important because it gives you information about the board itself. And that is very helpful because, like I said, a lot of the times you design a board, somebody else constructs it, somebody else assembles the board, and somebody else might maintain the board. So you would like to give them as much information about your specific board as possible. And that is the silk screen. Now we're going to talk a little bit about components and the different components we might use. As you might know, I mean, all electrical components, most electrical components come in a certain shape, and we have to know that information before we can design our circuit. Oh, that's a good point. I'm looking for my pen. Oh, my pen disappeared. Right, I'll have to make a note. All electrical components, let's have a look at these electrical components. Every single one of them would have a data sheet. All these components, even the smallest resistor to the biggest capacitor, to batteries, to controllers, microcontrollers, to PC chips, to anything has got a data sheet, which we'll have a look at in the next lecture, I think. I don't think we have time now. And the data sheet gives you information about what that component does, its physical dimensions, which becomes important because it will have to physically fit into the holes you make in your board, and loads it can carry, like how much current, how much voltage, how much wattage, what's the maximum temperature. So within a data sheet is contained all the information about our device that we want to use. And like I said, the smallest resistor up to the most complex Intel, AMD CPU chip, they all have their own data sheets. And these become very important. So I'm sharing my screen again. Now, I used to make a big fuss about different types like passive or active components, but it generally doesn't really matter that much. More in this course, it becomes a little bit more important if my component is surface mount or through hole and what type of loads that it can carry. I'm not going to talk too much about active and real components. So we now come into a thing that we have to talk about real and ideal components. So ideal components are used generally for calculations, but in reality, almost no electrical components adhere to their ideal rules. Let me just explain that for a short while. So when we are calculating the maximum current and power consumption and voltage and everything about our circuit, we generally use ideal components, meaning that if I have a resistor of 100 ohm, that resistor remains at 100 ohms. It does not differ from 100 ohms. It doesn't matter how long it operates. It stays 100 ohms. But in reality, it is very unlikely that your component, that resistor, would actually ever be precisely 100 ohms. And there are a various number of factors for it. Most electrical components, as we will go through resistors, has got a tolerance, meaning that it's a tolerance of plus minus 5, meaning that its value can be somewhere within a plus minus 5% range. So if you have a 100 ohm resistor, it might be somewhere between 95 ohms and 105 ohms. So that's a tolerance that components have. Now, you can choose components with smaller tolerances, but then the price of those components go up. Adding to that, there are a multitude of factors that affect your component. One of the most common factors is heat. If electrical components heat up, like they, invariably do, that heat causes them to alter their physical properties. So I'm going to keep using the resistor example because it's not like the easiest one to understand. But if a resistor heats up, its resistive properties change. It might go up, it might go down. It's very hard to physically calculate that. So to make things easier, we just say, right, we're using ideal components for our calculations, and we do not care, or we neglect all of the other noise or all the other heat effects or the tolerances. We don't really care about that. We only care about ideal because that makes our calculations easier. But the problem is a lot of the times you will create your circuits, you will test them, and for some reason they don't work as you expected. And that might be an element of your circuit or the ideal component not really functioning like the real properties it actually has. It's like the same thing if you're running on a treadmill in a gym. For, let's say you run 3 kilometers on a treadmill in the gym, that is one thing. That's like ideal conditions. But if you run 3 kilometers outside of the gym, it is a very much different experience. If you're running outside the gym, there might be a headwind, it might rain, you might go uphill, downhill, all that kind of things. And that is very hard to recreate that elements in a gym, for instance, to increase the realism of your run. So think about that in terms of electrical components as well. The components that we use in our calculations are most often ideal components that remain the same or react in an ideal way. But just keep in the back of your head that components in real life or in real circumstances sometimes change or deviate from that ideal behavior. And that is something you will always have to keep in the back of your mind, that although simulation worked, in a real environment, your circuit might behave differently. And that is why I also like to create prototypes on breadboards and on strip boards before I commit to create my final PCB design. Right. And we spoke about this as well. So like real, I mean, the electrical properties can be influenced by so many things. It can be temperature, pressure, moisture, interference from radios, noise. And there's so many things that affect our calculations that we just decided, you know what, let's just stick with our ideal relationships. And then we test our circuits and then test them in real life, see if they actually work. And this is also some elements might have linear and non-linear relationships. Some components, ideal components, quite often react in a very linear way, meaning that if I increase the voltage across a resistor by 2 times, then the corresponding increase in current will also be 2 times. That is a linear relationship. But in real life, it might look something more like this. If you increase the voltage by 2 times, the current will most definitely increase, but it will, in real circumstances, probably not be an exact increase of 2 times. There will almost always be some deviation. Right. We will have another 5-minute break. When then we carry on with the lecture. 5-minute break, drink a little bit of water, go to the toilet, relax a little bit, and then we'll see you in 5 minutes.